Hello everybody, my name is Rajesh Kaveti. In this video, I would like to introduce DynamoDB and give you a guided tour. We will go through some of the features of DynamoDB and the concept of provision throughput. We will walk through NoSQL data model and how one can use Amazon Web Services SDK to create that, and then wrap up the discussion with how you can integrate Elastic MapReduce with DynamoDB to do data analysis. So DynamoDB is a fully managed NoSQL database service. It offers seamless scalability along with an ability to do live partitioning. What that means is that it can scale up while it is running, and this makes it linearly scalable. That also means that it has predictable performance. This is achieved by two modes. One is that it has the concept of seamless scalability. In addition to that, you can get predictable performance using provision throughput, and we're going to talk more about that in later slides. DynamoDB does not have a schema, just like any other NoSQL, and that lets you have a very flexible data model. And that also means that you can add or remove fields without much of a ceremony. There is no cost to administration, and it also has the capability to do data migration to and from DynamoDB. Typically, in a relational database, when you want to do a data migration, it is fairly long and big project. But in case of NoSQL systems, particularly DynamoDB, it does provide you with quite a good level of capability to do that kind of stuff. Now, the latency of read and write is very low in terms of how it is documented in Amazon Web Services documentation. It is claimed that you can get a read and write in less than 10 milliseconds, typically ranging from anywhere from 1 millisecond to 10 milliseconds. So why do we need a NoSQL, or for that matter Amazon DynamoDB? So typically it's a classic problem that whenever in a traditional database, whenever the volume of the users increase or the complexity of the query goes up, the scale drops. And what that means is that the performance of the application drops as you try to scale up the application. So this graph kind of shows that same behavior where performance is going down as the number of users are increasing or the number of queries are increasing. Now this gap, which is usually addressed by adding more hardware or adding more of data sharding. Now while this can be achieved by adding new hardware, databases are not the greatest tools to support clustering, and you have to spend significant amount of money to get a delta benefit. So these solutions typically, if you want to increase more number of servers or you want to create more scalability within database, the cost of doing that is almost exponential. In addition to that, it is very hard to manage. So Amazon DynamoDB is based on partitioning and is essentially a distributed hash table. The performance, given that it is a distributed hash table, is predictable, unlike DB, and it is linearly scalable. And as I mentioned before, since it runs on solid state drive, it is extremely fast for read and write. Now, in the next set of slides, I will go over the DynamoDB database design. I will take a real application where I will display some of the operational tasks like query and updates. In that context, I will explain the data model, and at the end, I will wrap up this discussion with Elastic MapReduce. So, NoSQL databases, including DynamoDB, is based on a very simple key value pair model. So if you are a developer, you can see this as an associative array or a hash map. So consider this example where you want to insert an item into the table. Now you have to bear with me when I use these terms items and attributes, but Think of item as a row in a table. So the item has quite a few attributes. But you can see that the item that I'm showing you right now is a profile of a presenter, right? Where I have my name, I have my class, and I have given presenter as Rajesh Kavedi. Now, since every item needs a primary key, and here the primary key name is the name of the user with value as Rajesh Kavedi, or Rajesh for that matter. Similarly, class is another item attribute, and the value is CSIE Harvard. Now, let's say if I have another entry which is not who is not a speaker but an audience, and has another attribute called C. Now, in a classic relational database, you would have to go ahead and change the schema. Unlike RDMS, you can see that I do not need to create another table or migrate this data, but rather I'm able to evolve this table and just add another attribute. So recapping, and this is probably a good slide to give you what I meant by items and what are attributes. So let me recap this. All related collection of attributes are items, and items are grouped together to form tables. There is no limit on the number of items a table can store, which is different from Amazon SimpleDB. Data can be accessed using primary keys or primary and range key called composite keys. Composite keys are the only attributes that are indexed, and that means you can run queries only on range keys. So in this example, I can run a query to get data for customer in a specified date range. I can still get the entity using the primary key. So I can say, get me this entity using the image ID with image ID equal to 1. Or I can run a query where I can say, get me all the entities where the range key or where the specified date is between these ranges, and I can use that element to actually get the data set. So let me kind of go through the types of keys for primary index for query. And it is important because before you start creating a table, you need to make certain decisions on how you will store its index. DynamoDB has a key attribute data model where each item in the table can be retrieved by this one key. This key, called the primary key, has one attribute. So in this example that you see on the slide here, you can retrieve your item using name as the primary key. So I can say that give me this item with the name as Amazon S3. What I cannot do is get this item using category or thread as the basis. So the second one is the hash and range type primary key. So as I said before, primary key in this scenario is made up of two attributes, a hash attribute and a range attribute. So DynamoDB builds an unordered hash index on the primary key attribute and a sorted range index on the range primary key attribute. So in this example, a list of reply where ID identifies thread to which it belongs to, and reply date time is the range attribute. So I can get a list of replies which is in a certain date time range. So the example that I'm going to use in this presentation is a pretty straightforward one. This example is about a development forum where users can start various threads of a forum. On those threads, communities can reply. And I will use these tables to demonstrate some of the operational tasks. So you could have multiple forums on different topics, and each forum would have threads, and threads would have replies. So this is the basic relationship between these three entities. I also have a product table which I'm going to use for demonstrating elastic MapReduce. So in this example, as I mentioned, forum table has name attribute as the hash key and does not have a range key. Thread has a hash and range key, and the range keys are forum name and subject. Reply has a hash and range key. ID in this case is the key and is a composite of forum and thread along with the reply ID. And range is the reply date time. So at a very high level, this is the schema that I would be presenting. You have forum, threads are off the forum, and then you have replies off the thread. Okay. You can store data or attributes as string, numbers, or binaries, or you can store collection of that data set as well. So in the example that I'm showing you here, ID is a number, product name is a string, color is a collection of strings. An ID in this scenario is the primary key attribute and is of type number. And as I said before, color is a string set. Since Amazon DB uses hash key and range key to partition the data, let us first understand the best practices of how to assign hash keys. Good keys are well balanced across partition and uniformly distributed. So using keys like user ID are good candidates for primary key. Whereas device type, as shown here, is a bad hash key, as our popular devices will become hotkeys. So if hash keys are few, or there are many hot hash keys, then consider composite hash keys where you can concatenate some number that is intrinsic to the item. So if the item represents a person that has a device, calculate the hash key suffix from their name. So in a very simplistic way, here you have iPhone 5.a. So what I have done is concatenated a hash key suffix from their name. Now there are times when you load data from other data sources into Amazon DynamoDB. Typically, Amazon DynamoDB partitions your table data on multiple servers. So when uploading data to a table, you get better performance if you upload data to all allocated servers simultaneously. You might recall that DynamoDB uses partition and the data is actually spread apart across multiple servers. So suppose you want to upload user messages to an Amazon DynamoDB table. You might want to design a table that uses a hash and a range primary key in which user ID is the hash attribute and the message ID is the range attribute. So when uploading data from your source, you might tend to read all messages for a specific user and upload these items to Amazon DB. And what will happen is that since partitions are based on keys, one of your partition would get overloaded because you're specifically focusing on one user. So, and that may not be efficient. So what you really want to do is you want to load data across the user base so that you have better distribution. So in this scenario, you probably would want to load, let's say if you have 3 users, you want to load user 1, you want to load user 2 and user 3, and then probably again go back to user 1. And there are many other good practices to get the most out of it. And some are time series data, and there are other like use one to many tables, use multiple tables to support varied access patterns. So what are these? So if a data set in a time series that is being used a lot, it makes sense to move that data set to a separate table. That way other tables would not get impacted due to certain data set to be too hard. So imagine that whenever you actually create a table, you specify the provision throughput. Now, if you are working with a time series data and you are really interested in the last 3 weeks and you're not interested in the remaining data set, what you're doing is that you now would have to create a throughput, provisioning throughput for the entire table. Instead, you can take a subset of that data, which is hard, and you create a table and provide the right provision throughput for that table only. And all the archived data can go into another table, which probably would have lower throughput provisioning. The second example is use one-to-many tables. So if you store replies as an attribute value in the thread table, you would be constrained by the maximum item size, which would limit the number of replies you could store. So if you store replies as items in a table, you can store any number of replies because an Amazon DynamoDB table can store any number of items. But when you retrieve a thread item, you pay less for provision throughput because you're retrieving only the thread and not all the replies for that thread. So that is one of the reasons why you want to make sure that thread and reply are separate tables, and a reply should not be an attribute of thread. If you frequently access large items in a DynamoDB table, then you do not always use all the items larger attribute. So you can improve your efficiency and make your workload more uniform by storing your smaller, more frequently accessed attribute as a separate item in a separate table. So in this case, description is rarely changed, but it is pretty textual, whereas price can change more often. So you're better off creating a new table for price so that the amount of data that you use to read or write is less, and you probably can work with a lower value of provision throughput to update the price. You don't have to send the entire item, you would just send only 2 or 3 fields which would be stored in the price table. If it was in one table, you would have to send the item with the description as well. And as you're sending it, the DynamoDB is going to calculate the overall length of that item. There are 12 operations that includes creating table, updating a provision throughput, and deleting the table. You can do many item level operations, which include update, delete, create item attributes. One of the points that might be relevant here is that DynamoDB guarantees transactional consistency at item level. So if all attributes cannot be updated, the operation would fail. So in terms of getting data, DynamoDB has 2 get operations, and we're going to talk about that real quick. That is query and scan. Queries do searches on the primary key attribute, and it returns all item data for matching primary key till result set is exhausted or items have reached the limit boundary that user provided when executing the query, or amount of data has reached 1 MB of data. Amazon DynamoDB has a limit of 1 MB per query. So if your data set is more than 1 MB, then you would have to execute another query. Range key is the only indexed key in Amazon DB and can be used for filtering the data. In addition, DynamoDB has scan, where the table is first read and then the results are filtered based on the conditions that are provided by the user. Since it first scans the entire data set, it is definitely less efficient and far more expensive, since the scan goes towards the amount of data processed and is part of the throughput provisioning. So in query, if the data is not fully retrieved, you can use pagination features like last evaluated key to make another call. Now, one of the things that DynamoDB does provide is conditional writes. Now, in this diagram, what you're seeing is we have DynamoDB in the middle, and you have client 1 and client 2 retrieving the data at the same time. Now, what happens in this scenario is that client 1 retrieves the data, and sometime down the road, client 2 retrieves the data. Now, client 2 decides to update the data to some price. But what has happened is when client 2 was updating the data, client 1 also updated the data and changed the price from $10 to $8. So when client 2 is updating the data, that client is really updating a stale data. So in a traditional DB, you can easily reject this update. Now in NoSQL, the application will have to do some heavy lifting to get that logic correct. So DynamoDB provides an API that lets the client know what is an expected value that the client is expecting prior to putting or writing the data. If the data is different from what is expected, the API will throw an exception and reject the operation. So let me kind of give you a brief example of that in my right. So here what I have done is I'm gonna run the script, and what I'm trying to do is I'm trying to reproduce that same scenario where I have taken a data set and I have changed the value of that data set, but my expected value is different from what actually is existing in the database. And you can see that here, where I'm updating the value and I'm saying that the expected value should be 20, and I'm updating it to 25. Now what has happened is when I picked up this data set, the value of 101 was $2, and the expected value should have been 2. But just to demonstrate that, I made it $20, and you can see that I got an exception saying conditional check failed exception. So going back to the slide. The way DynamoDB, I've been talking about provision throughput quite a bit, and just want to give you a brief overview of what provision throughput means. So the way DynamoDB provides predictable level of performance is through an entity called provision throughput. This specifies the level of performance you want from your database by reserving the required I/O operations for your DB. So DynamoDB will reserve necessary resources based on your requirement, and this is a setup that you can either set it up during the start when you create a table, or you can reset later using console or using API. This is a pretty neat feature because as the volume increases, you can increase the throughput based on your requirement, and you can actually set up CloudWatch to follow or to monitor what is your required throughput. So whenever you actually break the ceiling of the throughput that you have provided, you could potentially have CloudWatch send you a message or a notification saying that you basically need to increase the throughput value. Sorry. So in DynamoDB, when you log into a console, you are greeted with this screen. You can select create table and give table name and nominate a private key. In this case, what I'm showing you here is you are creating a table, and once you create a table, you nominate your private key. The private could be a hash range, or it could be a hash. If it's hash range, you have to provide the hash attribute name, and you also have to provide the range attribute name. At the same time, you can set your provision throughput capacity. You can provide how much read capacity unit you want and how much write capacity unit you want. Now here I'm so that is one which is using the DynamoDB console. You can also do the same thing using AWS SDK. As I mentioned before, the AWS SDK for DynamoDB is very simple. There are less than 12 operations. There are actually exactly 12 operations that you can do using AWS SDK. And what you're seeing here is you essentially create for creating a table, you need to specify a key schema element with a hash key type, and then you need to specify the range key. Once that is done, specify the provision throughput for a read and write, and create a table request, and that's how you create a table. The same thing applies for uploading the data. You define your attributes, you create an item, you put the item request using the API with the table name. You put the item and you're done. Conditional check, as I said before, again you basically specify the item, you put the price of it. In this scenario, my expected price is 20. I'm trying to update to 25, and then I update the value. If my expected value is different from what the value of that object already exists, it's going to throw an exception, what we just saw in the demo earlier. Now I'm going to finally go over the Elastic MapReduce. Elastic MapReduce is essentially a managed Hadoop service, and it's a great tool for managing huge data chunks. It lets you do analysis on the data set. So if you think of Amazon DB or S3 as the collection of data, the Elastic MapReduce and EC2 are really responsible for the computation and collaboration, and that's how you actually get some of the real good features like importing the data from DynamoDB to S3 or HFTS, or you can import the data from or you can import the data from S3 to DynamoDB, and you can also use this feature to join the data. To set this whole thing up, I basically have a product catalog table that is an Amazon DynamoDB table. And what I'm going to do is I've already created an S3 bucket on the other side, and I would have to create two external tables, which basically would map the product catalog table. And then there's another table, the PCS3, which would map to the AWS bucket. So I already have a Hive. I already have the job started. So I'm just gonna type Hive, and that'll start my Hive script. I'm just gonna bring up my scripts so that I can cut and paste. And the first one, as you can see here, I'm just gonna wait for it, and my Hive is up and ready. So I'm just gonna take the first script, which basically creates the first table, and as you can see, it maps to the product catalog table. So let's see if it works. And looks like it's working on it. While this is working, let me explain to you what I need to do next. The next part is I need to create the second table, which maps to the S3 bucket. So this first one has mapped itself to my product catalog table. Okay. So the Hive has responded with OK. I can verify the existing, but I'm just going to skip it for now. Now I have created a table PC DynamoDB. The next part is to create the other guy. So I'm just going to take the script again, and this one is the PCS3, and some interesting points. You can see that it is mapping to my S3 drive. It is saying that the file, when it actually gets exported, the comma it's delimited by a comma. So I'm just going to do this as well, and I have that as well. Now I'm going to do insert here, and what that does is it's going to hopefully create a file in my S3. Okay, so while this happens, I'm just gonna go to my S3 and see what's happening there. Um, it's pointing to archive catalog 1, so I'm gonna go to archive my catalog 1. It's not there yet, so I'll just wait, hold on to it, and still working on it. It's doing the map reduce part, and hopefully it'll be done in a minute or so. Alright, looks like it's there. Let's refresh this. There you go. You have the and you have the file. Let's download the file. And there you have it. You can see that the file has been downloaded with comma as the delimiter. So we have actually done the first step. Let's go back to our PowerPoint. The second one is the native tables part. The second part, what I'm trying to do here is load the data from DynamoDB and execute a sample query. Now this query that's going to be executed, that will be stored natively. That means that it's going to be stored internally on the Hive table. So while uploading the data into DynamoDB, what happens is that if you actually upload the data into DynamoDB tables, it takes some provision throughput. But if you run the query on the data stored natively on the Amazon EMR cluster, it does not consume any of your provision throughput. So what happens is that basically means that I can actually run more complex queries, more involved processes without actually hurting my provision throughput. So I already have the external tables defined. So all I have to do is create these internal tables and then run the Hive scripts to actually show the data going back to this client. So I'm just gonna go ahead and find the script that I have for this. So I just need to create an internal table. Notice that I don't have external here. That means that I'm all set with this guy, and that was quick. And then I can just I'm going to upload the DynamoDB table data into this new Hive table using the insert statement. And it's working on it. This is going to take a while. And now the next step would be, the final step would be to run a query. I can query the native table using Hive, for example. In this case, what I'm trying to do is I'm trying to find the number of products in each category. Still working on it. Looks like it's almost done. So while this is running, let me kind of give you the advantage of doing this. It's very useful for complex queries or business intelligence reporting, where you have to do significant amount of data analysis, and it's also useful for data mining as well. And I think the biggest advantage is that you do not use some of the provision throughput, which is probably the most expensive element of DynamoDB. And here you have it. You can see that bicycle is 5, book is 2, book is 3, and that's pretty much what I have for this part. So the last slide I have is to cap. Amazon DB is a great tool. Um, it does have limitations, but none of these limitations cannot be overcome by choosing the right design. And that's all I have. Thanks for watching this presentation. Thank you very much.